So it's a great pleasure to introduce today's speaker, which is Allysa Lumley from CRM, and she's going to talk to us about primes and short intervals.
Okay, hi, thank you, Sean, for the invitation and the introduction. So I just want to apologize in advance. I received a puppy and my vaccine shot on Wednesday last week, so I'm a little bit tired. Waking up at 5 a.m. is hard. So some of you may know, but there we go. All right, so let's start. Before we get into the hairy details of what's going on, of course, everyone should understand the question that we're actually trying to answer with this paper, right? So everything starts with Gauss when we're talking in number theory, right? So Gauss, around the age of 15 or 16, said that within a neighborhood of X, the density of primes should be about 1 over log X, right? So keeping this in mind, the reasoning suggests that if we look at this difference of pi of X plus Y minus pi of X, that the number of primes we would find in this interval, where we're inclusive on the X plus Y and we exclude the X, is roughly Y over log X, okay? But anytime you make a statement like this, you should start asking yourself, okay, well, how big is X? How big is Y? Because something like that is not always going to make sense, right? So supposing X is super large, maybe even going to infinity, for which Y values does this statement make any sense, right? So if Y is too small, like fixed at 1 or 2, or even fixed at any number, and X is going to infinity, then of course the statement is kind of silly. It doesn't really make a lot of sense to say that, you know, there's 0 primes in the interval. So if Y is large, say that it's a power of log X, so it's growing with X, where we take C strictly bigger than 1, then you can imagine that, yeah, this actually makes a lot of sense, right? Based on the density, all this kind of thing. So then there's this intermediate range between being a constant and being a power of log X, where you might ask, like, okay, what if it's a constant times log X, or even a little bit smaller? How does pi of X plus Y minus pi of X grow? And in this particular range, we need to think a little bit more deeply, really, about what's going on than just sort of applying this simple heuristic, okay? So what do we know about the difference of pi of X plus Y and minus pi of X? Well, in the 40s, Selberg showed, you know, a quite strong result under the Riemann hypothesis, that if your Y is growing, is increasing, such that Y is still less than X, but the ratio of Y of X over log X squared is still going to infinity with X, then for almost all X, we can say that this difference is asymptotic to Y over log X, okay? So basically confirming that reasoning that we had at the start. But of course, there's a very big caution when you see a statement like this. The caution is that almost all is not equal to all, right? And the question that we're interested in is not really just how many primes there are in this difference, but we really want to understand what is the maximum number of primes we can get into an interval of this length, or the minimum number of primes in this length. And of course, at that point, the behavior can become quite extreme than what is the asymptotic ideal. We might get intervals that have quite a bit more than Y over log X primes, or we might get intervals that have less, right? So this is the question. We want to understand what is the max and min behavior. And that's going to be the focus of the rest of the slides going forward. So with this in mind, we should think about this as like the question about how Y is a power of log X is growing like a power of log X, and in particular that the power has to be greater than 2, right? So that was the sort of dichotomy of the questions that I had before. So later in the 80s, Meyer proved a different result, which seems to be a contradiction to the asymptotic thing, right? Because you get that if you fix A larger than 1, you can find a positive delta and some X plus minus, which are arbitrarily large, such that if you look in an interval of length log X to the power of A, that this difference is actually greater than log X to the power of A minus 1, so bigger than Y over log X, bigger than 1 times Y over log X, which is what, you know, the asymptotic is telling you, that it should be a 1 here instead of a 1 plus delta A. And we have the similar situation where if you look at the difference, you can get that you can find intervals with the coefficient being 1 minus delta A. And so again, the constant is wrong. Okay, but of course these are not contradictions, because the previous slide we already said that Selberg's result is an almost all statement. So what he's really doing is picking out some of these weird behaviors, the ones that we are interested in understanding for this talk, right? So it turns out that when A is larger than 2, we believe that, you know, if you combine Selberg's almost all result and this theorem of Meyer, that this tells the whole story, and this is really how this difference behaves, okay, for the max and the min and the growth, the asymptotic behavior. So what is at odds in this situation then is what's happening if, you know, you take a power, or you take your interval to look like log x to the a, but the power is between 1 and 2, or what happens if you take it to be smaller than that? What's going on in that scenario? Okay, so we'll introduce some notation here. The players in this talk are going to be capital M of xy, which is defined to be the maximum of pi capital X plus y minus pi capital X, where we let this capital X range in this interval from little x up to 2x. Okay, so we're going to let this go over, and then we want this to spit out the largest number of primes we could get in that interval. And then similarly, although the focus will be on capital M, we might get to talk a little bit about little mxy, which is now looking at the same thing, but for the minimum. How few primes can we fit into an interval of this length? Okay, so a summary of the above discussion, combining Selberg and Meyer together, is saying that if y is greater than or equal to log x to the 2 plus epsilon, we think that the min and the max should be about the same size, and that they look like y over log x. Okay. So again, just reiterating, so what we're still not clear on, and what the focus is how these quantities behave, is if y is qualitatively smaller than log x squared, or even just a constant times log x squared, right? Because this, we got the plus epsilon there. So how do we approach this kind of question? Well, we need to introduce a little bit more notation just to make sure everybody understands. So the first thing is that we define this set Sxyz, which is counting the number of integers in the interval x plus 1 up to x plus y, such that m is co-prime to all the primes less than z. That's what this p of z here is, and we wrote this notation here. So you can think of this as that we're trying to sieve out by the primes that are small. Okay, so z is some parameter, we're sieving out by the primes that are small in order to reduce the space that we're searching for these primes. Okay, and then we define here s of y to be equal to the maximum value that s capital X yy can take, where we let our capital X go over x and 2x. Okay. So clearly, just looking at this definition of Sxyz, we can see that the difference of pi x plus y and minus pi of x has to be bounded from above by Sxyy. It doesn't make sense for it to get larger than that. So we can deduce, you know, that if we take the maximums of both of these, that mxy should be less equal to s of y, right? This is a sort of straightforward idea. And again, here, this is with y fixed, okay? So if we want to understand what's going on with our mxy, we might then think, okay, well, why don't we actually study instead this s of y? Maybe this is an easier thing to understand than the mxy, right? So what sort of information will we need in order to understand that? Well, there's a very famous conjecture of Hardy and Littlewood called the prime k tuplets conjecture, which just says that if you have a1, a2 up to ak being an admissible set, so that you could potentially get infinitely many n's, such that n plus a1, n plus a2, all the way up to n plus ak are going to be prime. That's a statement of the conjecture, that there exists infinitely many n's satisfying this result. So if we believe their conjecture, which is quite a strong statement, if we believe the conjecture for y fixed, and we look at the maximum of x greater than or equal to y of this difference that we're studying, it should really actually achieve equality, that we're going to get s of y here, okay? And this reasoning comes from the fact that you can think about s of y as being the largest admissible set, which is contained in some shift of the interval 1 up to y, okay? So you expect that this should be the maximum size for this interval. All right, so if y is fixed, the k-tuplets conjecture kind of says this is what it should look like. It should look like the size of a maximal admissible set of length y, right? All right, so good news. We seem to have some foundational, or at least believed ideas of this equality. And of course, anytime you set one thing is equal to the other, you would hope that that new thing is something that you understand and that you can actually say something about the growth, right? So what can we say about S of y? What do we know? Well, if you recall this definition of the Sx to yz and then the S of y, the best known upper bound that we can get, which is essentially a Brun-Titchmarsh result, is that S of y is less equal to 2 times y over log y. Okay, so there's this coefficient 2 in front. And the most extreme examples that we can find, giving a lower bound, is that S of y is greater than or equal to 1 plus some little o of 1 times y log y. So there's some contention about what's going on here. Which of these bounds is actually correct? Do we expect the coefficient to be a 1? Do we expect the coefficient to be a 2? And how is this supposed to play out in the long run? So the trouble with this particular upper bound here is that we had hoped that if we switched our focus from mxy over to S of y, that we could get somewhere and actually understand better the upper bound. But this Brun-Titchmarsh thing, you know, we don't have much hope of improving it without making progress on like Siegel zeros, right? Making progress on GRH. So it seems like actually we're stuck again. So this is kind of annoying because the new thing that we wanted to study also is very hard to get a handle on. It turns out, though, that we do believe that this is the correct answer, of course. And so we actually think that S of y, should be like y over log y here, so that the coefficient is a 1 instead of a 2. This is what we think. And this is, in fact, what we think our mxy is going to look like, too. Okay, so that was all of that analysis was being handled where we take y as a fixed number. Okay, so what if now, instead of letting y stay fixed, we study what's happening in this range if y is actually growing as a function of x? So what should happen, and how long does this conjecture of mxy equaling S of y hold for? Well, we expect, based on a couple of things, that this should work for all y less equal to a 1 minus little o of 1 times log of x. Okay, so the justifications in the paper are that we have two different probabilistic arguments for this. There's a Kramer probabilistic argument, which I can hopefully get to at the end. And there's also a careful study of the range of uniformity for an explicit version of the prime k-tuplets conjecture. Okay, this is extremely technical, so I'm not going to focus on that today. And we also have some computational data, which makes us feel like, yeah, this actually makes sense. Okay, so let's take a look at the pictures. What kind of data do we have? What sort of stuff can we say about it? I posted up two graphs. So one of them is mxy versus S of y, where we take little x to be equal to 10 to the 11. So just to remind you, we're taking the max over the interval pi of x plus y minus pi of x, where the range of variation is between x and 2x here. Okay, so we're going between 10 to the 11 and 2 times 10 to the 11 in this first graph. Okay, so let's see if I can zoom in a bit so that you guys can see it a little easier. So what's being plotted here is that these blue dots are the actual prime counts that we found, the maximum prime counts that you can get in this interval. The x-axis, somewhat annoyingly, is plotting the y values. So as we increase the length of the interval, how many, and then the y-axis is plotting the number of primes, the maximum number of primes that you can get. So that's what the blue dots are representing. And then the square ones here is actually the largest admissible set of the same length, of length y. Okay, so you get S of 2 here has only 1 prime, and in fact the maximum is only 1, and etc. all the way onward. Okay, so the behavior seems to hold for quite a while, actually. And if we shift over to the second graph, it's the same, plotting the same information, but now we've increased our little x to 10 to the 12. So we're looking in between 10 to the 12 and 2 times 10 to the 12 passing over these intervals throughout the whole range. And we have the same sort of thing, that these blue dots are landing exactly into these purple boxes, which is counting our S of y, okay? So the only thing that I haven't really explained about the graph is what is this dashed line here? Well, this here is telling is log of x. So this is where we believe that the conjecture should hold up to, that all these blue dots should in fact land inside of the square boxes up to this dashed line. Okay, so computationally speaking, it looks like actually it's going to go for quite a bit longer, like a constant bigger than 1 times log x. But this sort of, if this is to persist and hold out for x larger and larger, then we might actually see something weird happening in the heuristic. So we don't think that the constant should be bigger than 1, but in the small numbers that we were able to calculate, it does actually fit for a lot longer. Okay. So before we go, is there any question about what we've talked about so far, or we're okay? It's good. All right. So this is the situation if we let y be less equal to 2 log x. Okay, so I plotted all the y values up to 2 times log x to compare with what's going on and try to understand that. And again, the conjecture is that we think it should hold up until 1 times log x, that it's equal to S of y there. So what's going on in this situation? What have we already observed? Okay, we had at the beginning this behavior that was combining Selberg and Meyer's result, which was saying that if y is bigger, just bigger than log x squared, like growing just a little bit faster than log x squared, then we expect that mxy is going to look like a y over log x. That was sort of the summary of those two results put together. And the previous stuff, the stuff with the computational data, said that if y is just around the size of log x, so 1 less power, we expect that it grows like y over log y, which is really looking like y over log x for us, right? Because x is around that size. So if you think about it, like if I was to double the size of my interval, if I multiplied y by 2, I would get double the amount of primes in both of these situations. And so it looks like really these are both linear in y, right? But the slope that we're observing is extremely different in each case, right? On the one endpoint, the slope is y over log x, and at the other endpoint, the slope is y over log x, okay? So what's even more interesting about this is if you study an interval, say, which is x up to x plus this y log x to the k here, you get this phenomena where if you go from having a k equals 0, so you start at 1 and then you go up to, or you go from x to x plus 1, you should expect at most 1 prime. If you go from x to x plus log x, we get roughly a jump in size log x, right? Log x over log x. This is essentially a jump of size log x. If we go from power of 2 up to a power of 3 in the length of our interval, we get a jump of log x. And if we increase again by another factor of log x, the length, we get another jump in the number of primes by a factor of log x, right? And this continues forever. If we keep looking further down, that's the behavior that we expect based on Selberg and Meyer's results. But what's going on here between interval of size log x and an interval of size log x squared? We only get an increase of log x primes, which is very strange. Like, why is it so small in this region? So this was sort of the starting point, or about the research, like what's going on? Why is there such a small increase in primes in this region, in this jump in the length of the interval? And then the next natural question to ask is that since these are both linear in y, we'll say roughly linear in y, we want to understand what's going on in the transition. Is it still linear, just with different slopes? Like, what's the behavior of this growth where we're in the middle? Instead of increasing by a whole power of log x, we increase a little slowly, okay? So the proposed transition that comes out of the heuristic is that if we take y to be log x to the a, where the power of a is now strictly between 1 and 2, so the region where we are confused, that mxy should be asymptotic to 1 over 2 minus a log x over log x. So quite clearly, it seems to no longer hold this linearity in y. the linearity in y seems to have disappeared. And in fact, now it depends more on what the logarithm of y is. Okay, so the thing that's changing here is the a as we increase. So we can actually give a more precise statement than this one. And when we compare with the data, we use this more precise system, which is that we define this lxy to be log x over log of log x squared over y. Okay, and we conjecture that if log x is less equal to y, but y is still little o of log x squared, then mxy should be asymptotic to this new function, this lxy. Okay, so that's the claim. What is the justification for this? Well, it's tied into that Primek heuristic that I mentioned at the beginning, or when I was talking about the other interval. And also we have a little bit of data, right? We can kind of see what's going on. But the graph is a little strange, okay? So again, if we're looking, I'm doing this for 10 to the 11, that's my x value, and I'll show you the 10 to the 12 one in a second. This time the blue dots are again the actual data, the actual maximum number of primes we could get into these intervals of specific length, the x-axis plotting the length of the interval. And the green line now is plotting our LXY. So you can see that it's pretty close in this sort of range. Okay, it looks fairly close, although there's a bit of a weird change in concavity that's happening in the graph right here in the middle. This one looks kind of concave up, and this one looks concave down. So that's sort of a weird behavior, which we can't really explain at the moment. This dashed line is again placed at log x, just so you can see where there's some kind of transition in the behavior. They seem to cross each other at log x, and then they cross again somewhere else over here in the log x squared range, some constant times log x squared, some constant less than a half log x squared, because that's the range of y values. We don't go beyond a half of log x squared because in fact this lxy goes off to infinity quite quickly. Like as soon as you increase, I want to say past like 2/3, it becomes an incredibly bad guess for how big this is. And the sort of fact that we're going between 1/2 log x and 1/2 log x squared is just this little o notation is not really clear how to interpret. So remember that the conjecture was that it should hold for all y equal to little o of log x squared. But when you're dealing with explicit stuff and the x value is incredibly small, right? Like asymptotics don't usually kick in at 10 to the 11. It's sort of hard to know exactly how far we should look at the graph. But yeah, so that's the reason for the weird range. And of course, we also have the data for 10 to the 12, which is looking very similar. Okay, so it seems to cross the actual data, the prediction seems to cross the actual data around log x, and again, somewhere at some constant times log x squared. And again, their concavity is weird, right? So I think I already said that. Yeah, we're not sure how to explain the difference in the concavity here. It's somewhat mysterious at this point. Okay, so before we actually, I think I have, yeah, before we go on, are there any questions so far about what we've talked about? Okay. So just to summarize and catch everybody up, what we think is happening is that there are actually 4 distinct ranges for the size of y, where mxy is going to behave differently. Okay, so there's the range where y is bounded by some constant times log x, and this is the one where we think it looks like the maximal size of an admissible set, which is, we believe, y over log x. Okay, so that's the conjecture. There's the situation that we just discussed where log x is less than y, but y doesn't go larger than log squared x, which we think is this L of xy situation, which is now depending on the logarithm of y rather than y itself. And there's the situation that Selberg and Meyer figured out for us, Selberg, Meyer, and they say this is asymptotic to y over log x, okay? So there's this one last range in the very middle, which is that we think that the behavior where y is about a constant times log x squared is going to be distinct from all three of these other ones, right? So this is what we haven't discussed yet, and that will be coming up on the next few slides. So then there's also the secondary question about, I talked a lot about the capital M of xy, the maximum, so what about the minimum? Why didn't I say anything about the minimum until now? Well, as in these particular cases, we think that mxy is going to be 0. And so there's nothing interesting to say. We don't want to bother spending energy looking at that. And in this case, the Selberg-Meyer results combine to give us basically the behavior, right? So the only situation where little mxy is actually interesting to study is this third one, where things are sort of up in the air. Okay. So, did I say everything? Yes, excellent. So let's talk about that remaining range, the last guy that we haven't discussed. We suppose now that y, the length of our interval, is equal to t times log x squared. Okay, so we're conjecturing based on the heuristic that mxy is now asymptotic to some funny thing here, u plus evaluated at c plus t times log of x, where u plus of t is strictly greater than t. Okay, so wherever, wait, what do I want to say? It's the solution to this equation, sorry, u plus evaluated at t is the solution to this equation where we take the choice that u plus of t is bigger than t, because there are going to be two solutions to this thing, one that's smaller than t and one that's bigger than t. And we think that the maximum is going to be predicted by the one that is actually larger here. Okay, so we think it grows like a constant times log x, and the constant is depending on this equation, the solution to this equation. So now you might say, okay, well, what is the C plus? Where is this coming from? And this is coming from a question about sieves. Okay, it's a sieving constant. We probably won't talk too much about it, but I will mention just that at present, we do not know the exact value of C plus, and we are only able to show that it should be greater than or equal to 1.015 ... Okay, so in order to compare with our conjecture that we think it should look like this, we're going to just take C plus to be equal to 1.015 for the remainder of the slides, even though we are not sure exactly what its value is going to be. Okay, so we have our data, again, just comparing what's going on. We compare the mxy versus what we think it should be, constant times log x, and the C plus is fixed on the last slide. And now the range for our y values, aka the x-axis, is that y always takes the shape t times log squared x, and we're just letting our coefficient t range between 1/3 and 2. Okay, and again, this is sort of a random choice of values based on what we could actually compute, and also where we think things should start to shift away from that little o log x region that we couldn't pin down the exact constant for. So if we zoom in to look a little bit carefully, again, this is the plot for little x being equal to 10 to the 11. And we're looking at all the intervals between 10 to the 11 and 2 times 10 to the 11. This graph here, I don't know if you can see the color. These are still blue dots, but there are so many of them now that it just kind of looks like a black line. This is the actual data that we were able to calculate. And this pink line, the magenta line, is describing the growth that we conjectured, the u plus times log of 10 to the 11. Okay, so as you can see, there's a significant gap between the prediction and the actual data, and this persists actually if you look in an even larger range where you're taking your little x to be equal to 10 to the 12. Now you get the same sort of huge, I don't know, widening of this gap, where it appears to be widening to my eyeballs right now. I can't really prove that. So what's happening? Well, the prediction, so the purple one or pink line here, is too large by about 35%. That's what you can just guess based on the actual values. You can look at the ratio. And this is somewhat disappointing, actually, if you think about it, because I just told you on the last slide that C plus has to be greater than or equal to this 1.015. And if it turns out that in fact C plus is larger, like if it increases, that this gap is actually going to get bigger. We did plot a few other things, and you can prove it actually that it will become larger. So this is sort of a bit disappointing that the gap is so big. And I also did run some very small experiments with really tiny x equals 10 to the 8, x equals 10 to the 9, where we let y range between 2 times log squared x and 10 times log squared x. And if you looked at that data and you looked at the ratios to see how far away the prediction is from the original, the gap shrinks considerably. Like it goes down to maybe 15% or something like that. But these are very small x values, so we're not making any claims that this is something that should persist, right? Okay, so I think I covered everything I wanted to say about that. Yeah. Okay, so this is the situation for the maximum when you take y to be about the size of log x squared. So I said that the other thing that's interesting in this range is to actually look at the minimum. So we want to understand what should the minimum look like. And it turns out that that same equation that we saw on the previous slide, this u times log u minus log t minus 1 plus t equals 1, it gives us the prediction that we want for the minimum as well. Okay, so this time we think that the growth of our mxy should be given to us by figuring out what is u minus of t and multiplying it by the log x. We think that this should be asymptotic to this constant log x, where we define u minus of t to be the solution to this equation, which now goes in the interval 0 t. So it takes the other solution that falls out of the equation. Something important to note is that there is in fact no solution if t is less equal to 1. So in that scenario, we set u minus to be equal to 0. And this is sort of, not sort of, is related to the maximum gap between primes that we expect to see. Okay, so what is left is the c minus. Where is the c minus coming from? That's inside of here. And it's again just another sieving constant, which we do not know the precise value of. Okay, the best that we can say about c minus is that it is no larger than e to the gamma over 2, which is equal to this 0.8905. Okay, dot dot dot. So that's the situation, and or what the heuristic suggests. So what about the data? What can we say about our guess? Does it make sense? Is it following, you know, the truth? Okay, so again, same x values here. We look at these blue dots, just like before, they're actually plotting the minimum. That's the exact value that we expect to find. And this red line is plotting the prediction. Okay, so you see that the value stays, our prediction thinks that we should actually have large gaps between primes for significantly longer than the data shows. Okay, so this jump is happening much earlier than we expect it to happen, and this kind of persists as we go forward in this data. You can see I put this dotted line here at 3/4 of log x squared, just so that we could kind of see that as we do increase the x, that the blue stuff does go more that way. It seems to be growing. It seems to be lining up more with what the prediction is saying. Okay. So this, for me, when I first made this graph, I was actually extremely disappointed because not only do we have this thing where it stays 0 for much longer in the prediction that we expected, we already have this as an observed phenomena that we haven't been able to actually find what we believe to be the true maximal prime gap size, which I'll talk about a bit in a second. But what I was really annoyed about is that it's also not clear that if we look at this growth, if the data is even following that shape. Like it's not actually clear that the shape is the right shape from this picture. Okay. All right. So what's really interesting here is where the mxy is equal to 0, as I've already said. So what is the reason that this red line is going so far? Okay, well, I told you that the solution to that equation from the previous line, u minus, is going to be 0 if our c minus times t is less equal to 1, right? So if we take c minus to be e to the gamma over 2, then we expect actually that we shouldn't see any primes, or the maximal size of the prime gap is going to be 2 times e to the minus gamma log squared of x, okay? So that's why the extension goes for so long, and that's exactly where it starts to curve up in each stage, is that when we hit this 2 e to the minus gamma log squared x, we transition from having no solution to having positive solutions that we can talk about. Okay. Yeah. Okay. So then, as I said, this early jump here in the blue data going above the red line is an observable phenomena. It's been studied by several other people, and it shows up a lot when people instead focus their attention on the maximal gap between primes. They're not looking at little mxy in particular because they're not worried about how it grows afterwards, but they're studying the maximal gaps between primes. Okay, so I sort of already said this, but let's put it down appropriately now, that we expect the maximum that Pn plus 1, where Pn plus 1 is the n plus first prime, minus P of n should be about 2 to the e minus gamma times log squared x. And it is feasible, the heuristics predict that we really think this should become an asymptotic equality, that we should be able to say something stronger. We haven't really conjectured that, but we think that it's feasible, that this should be an asymptotic here. But the data we have so far is really not that convincing. Okay, so I think I stopped my calculations around here because the question that I was studying is a little bit different, and I couldn't compute that far. But people have looked at these prime gaps for very large values of x. I can't remember how big this is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15. So this is 16 digits long, okay? And the largest gap they found is 1132, which is about 92%. So if we would expect the coefficient to be 0.92 and not, something bigger than 1, which is 2 times e to the minus gamma is bigger than 1. So we can't even find a prime gap that satisfies 1 times log squared of x. And yet we persist. We still believe that actually we expect this to happen eventually. Okay, so just for fun, I guess, we can say we sort of graphed the two different, the heuristics against the data, and then we did some like best fit plotting just to see what would come out of it. So the blue line is the heuristic, what our heuristic suggests, and I think Granville also conjectured this in a separate paper a long time ago, maybe 20 years ago, that he expected the maximal gap should be around this size 2. The orange line has to do with Kramer's original model that we have modified for this paper. And so it's got a coefficient of 1, so that's what the orange line is here. And then these blue dots, the scattered dots, are the actual values that are plotted from that table that I just showed previously. Yeah, so again, just for fun, we made a graph with a green line and then a red dotted line here, which is a best curve fitting if you allow some extra careful accounting to go on, where you get these sort of additional terms in your asymptotic. But the main point here is that the green one is dealing with a coefficient of 1, so in line with the original Kramer heuristic, and then the red dotted one is having the same coefficient as the one that we use in this paper. Okay, so they do fit like remarkably well, and it was just sort of pretty, so that's why we included the thing. It doesn't really say anything about the truth, but it's fun. Okay, so that's that. All right, so now we'll talk about this mysterious heuristic that I've mentioned several times now. Before we go forward, though, are there any questions about the data, about what's going on, the ranges, etc.? No? Okay. I do have a question for the organizers. Am I supposed to stop at 12:50 or at 1? Oh,
Yeah,
sorry,
I think
5.
yeah, 55 minutes past, and
Oh,
then
55 minutes past.
leave
Okay, so
5 minutes for questions.
perfect. Perfect. Okay, so what are the ideas behind this? Why are we making these conjectures? Where does it come from? Well, we'll sort of start with the basics of where this probabilistic analysis of primes came from in the beginning. So you start with Gauss, as we did. He has that the density of primes about x is about 1 over log x. So Kramer used this as a jumping point to say, okay, well, instead of looking at the primes, let's just consider a sequence of independent random variables, xn, where n is greater than or equal to 3, such that the probability of xn being equal to 1 is 1 over log n, and the probability of xn being equal to 0 is the remainder, 1 minus 1 over log n. Okay. Then he says that any properties which occur with probability 1 plus little of 1 for his independent random variables should also hold for the sequence 1, 0, 1, 0, 1, 0, 0, 1, 0. And I don't know how comfortable you are with recognizing this, but this is in fact the primes themselves. So this is 3, 5, 7, 11, etc. Okay. So he's saying, you know, if this sequence of random variables satisfies this property, we should expect then the primes will also satisfy this property. If you can imagine that the primes are independent and they behave randomly and that kind of stuff. Okay. So for example, with probability 1 minus some quantity which goes to 0 very fast, then the sum of these xn's, if we sum them all up until capital N, gives me this integral. Okay, so the prime integral that we expect, plus an error term of size n to the half times log squared n. Okay, so from this hypothesis of Kramer's, he's saying that in fact pi n looks like our logarithmic integral plus this very nice error term, which people should recognize as coming from the Riemann hypothesis. So his idea seems to predict the Riemann hypothesis, right? Like we really think it's a very valuable question to look at or try to understand the, plan of attack to try to understand these questions because it does predict some very important things. Okay? However, there is some obvious flaws in this heuristic of Kramer's, okay? So if you think about it from the perspective of like twin primes, based on Kramer's idea, we know that all the xn's are completely independent from each other, right? So if we look at, I guess the expectation of what you have xn times xn plus 1, sorry, the partial sum of this, xn times xn plus 1, we're going to return back this integral, which we expect to see in the twin prime conjecture with some error. But this is now predicting that infinitely many primes will appear of the form n and n plus 1. Not only that, you can sort of interpret it to say that it's suggesting that half of the primes should be even, which doesn't make any sense, right? Like we know that there's only one even prime, and so there is a serious flaw in the reasoning or in the hypothesis here. Okay, so what is the flaw? Why is it giving us such a funny statement? And the reason is that it is completely ignoring divisibility by small primes. Okay, so it's not taking into account that, you know, if you're divisible by 2, then you're not a prime, right? So it's completely removing the fact that in fact that integers do have some dependence on each other, and so we can't 100% say that they're just completely independent random variables. Okay, so what's the idea? How do you fix this flaw? You first pre-sieve by the small primes. And then after you've done this pre-sieving, you have a new set, which has a bunch of numbers which are not divisible by any of the small primes. And you can use a new probability to guess which of those numbers, or sorry, not guess, what's the probability that one of those numbers out of your new set is a prime, okay? And you can derive a new binomial model, just like the one that Kramer has, but it has a different probability, okay? So for us, how far do we sieve? Well, we just try to remove integers which are divisible by primes less than some constant times log x. That's the length of our sieving. Okay, so what happens now? We have a modified Kramer, a new binomial model to predict what's going on. We consider now our independent random variables again, xn for n greater or equal to 3. But this time the probability that xn is equal to 1 is going to be p over phi of p times log of n, where this is the Euler phi function here. And again, this p, just reminding you from last time, is all the primes, the product of all the primes up to z, our sieving stopping point. Okay, so you change the probability based on the primes that you sieved out. And again, then probability of xn being equal to 0 will just be the remainder of what's left over. Okay, so if you do this, if you do the same kind of binomial or the same kind of analysis as before, it predicts things that we couldn't predict using Kramer's model. For example, this thing will give you the prime number theorem in arithmetic progressions. It provides not only a prediction of RH, but GRH, the generalized Riemann hypothesis. It accurately tells us what twin primes should look like. And at least in the main terms, gives us some idea of the prime k-tuplets conjecture. It's predicting this prime k-tuplets conjecture as well. Okay, so the old model was telling us, and this point here is a focus of a paper of Andrew before me, 20 years ago. The old model was saying that the difference between pi of x plus y and pi of x would be asymptotic to y over log x all the time, right? For every x, for every y larger than log x to the power of 2 plus epsilon for all the y's. And you wouldn't find any weird counterexamples to this asymptotic, but of course we know that Meyer found some. Okay, so the original motivation for a modified Kramer heuristic is to look at trying to account for these extra primes that Meyer found. And this is work that Andrew did originally, that this new model does actually predict this accurately. It says that, yeah, sometimes you're going to get more primes than you expect. It can happen. Okay. Yeah, okay. So now that you have this idea, we're making these conjectures based on this probabilistic reasoning. Well, what is actually the effect of the sieving, what's going on, and what are the limitations that this new model has? Okay, so I've just been saying, like, it's pretty great, it predicts a lot of stuff, but of course, there are questions revolving around sieves that are actually unresolved. And so you have to sort of tackle those and try to fight with those to understand if, you know, how good your prediction is. Okay, so we just recall that after we sieve, we get this set Sxyz, which I introduced way at the beginning. Again, it's just counting the number of integers that land between x plus 1 and x plus y that are co-prime to the product of all primes less than z. Okay. So how big is this Sxy? This is a question that we need to know if we're going to understand what is the probability of something randomly picked out of there being prime. So let's make some guesses. We said that, or not guesses, analyses. We said that little z should be taken around the size of log x, and that's how many primes we're going to sieve out by. And we're looking at y being the length of our interval around size log x to the a, right? So this is the question that we've had the whole time. So typically speaking, you expect that Sxy should look like this, right? You just remove the primes that are, you don't want to be divisible by the primes that are less equal to z, and then how many numbers did you originally have? This is what you should get. So what do we need? We actually need to understand what are the bounds for Sxy and the typical size. Like, what's the actual ratio? And this is a classic sieve theory problem, which I already said is not entirely solved. We don't know actually how to attack this. And this is somewhat where the limitations of the paper come into play, and maybe why some of our data is a little bit spotty. Okay, so what's happening if you suppose that sigma minus of A and sigma plus of A represent the best possible bounds for this ratio? Okay, suppose that we can get a lower bound of, the best lower bound we can provide is this, and the best upper bound we can provide is this, where we let y be log x to the a, and we're varying over our x's. This is sort of informing where those sieving constants are going to come from in the data, like the C plus and the C minus. This is where our C minus would come from. This is where our C plus would come from. That's the gist of that explanation, okay? So you might ask yourself, all right, this is an inequality. Can we win a little bit? Can we provide better results by showing that this is actually strict or not, right? There's this question there. And unfortunately, there is a more general question in sieve theory, which tells us about the size of these sigma minuses, or sorry, sigma minus A and sigma plus of A. We know, the smallest they can possibly be and the largest they can possibly be, where this is a Dickman-de Bruijn, no, this is the Bookstabe equation, and this is the Dickman-de Bruijn differential equation. They're delayed differential equations, okay? So in the most general framing possible that you could ask a question about how large a sieve set is, the most general set you could look at, it turns out that these inequalities are achieved, that we cannot get any better than these estimates, okay? So this is somewhat disappointing, but the work where they found that this is in fact an equality, what they did is they took the general sieve hypotheses and they just created a set which would meet all of those hypotheses, and then did get these extreme values for the constants. They found these sets, okay? And the set that they found, the set that they constructed, was not an interval. So we're looking at an interval. So maybe there's some hope that we could actually get some improvement on this sieve. Unfortunately, in a separate work that Andrew did concurrently to this one, he proved that if we were to make any progress on this question about whether or not these extreme values are achieved in an interval, I'm over time. It's in fact optimal if we know that there are Siegel zeros. Okay, so if there are Siegel zeros, then we can find intervals where these sieving constants appear, and you can't get any better. So that the mxy is bounded above by sigma minus times y over log x, and the capital Mx is bounded from below by sigma plus times y over log x. Okay, so I should stop because I already went over time. I'm sorry about that.
Take a few more minutes, honestly, if you know the end.
Okay, it's only a couple more slides and they're mostly pictures, so we'll see what's happening. Okay, so we're in a place where if we want to make improvements on the prediction and how good we can get from this heuristic, we need to make progress on GRH. So that's the same problem that I mentioned at the beginning with studying S of Y, that we need to make progress on GRH in order to actually get something better. So this is sad, but maybe there's still some hope. We can test the validity of the model in a different way. Let's just actually look at some data and see how close the prediction, like the binomial curve that our probabilities would give, that our probabilities would give to the actual data, okay? So in order to do this, we had to look at a much smaller x than before. We had to look at x equals 10 to the 8, because it's incredibly computationally heavy. But that being said, we still get to observe some nice behavior, okay? So we're gonna take our x to be equal to 10 to the 8, and we're taking our y value here to be around log x squared, so that's the length of the interval. And this, in this case, is roughly, 340. And we're gonna sieve up to 11. Now you might notice that this is not square root of 340, but it turns out that, again, it makes it very computationally heavy if we try to sieve out by even more primes. So we just tried 11 to see how good it would do. Then, computationally speaking, we can find the exact size of these SX, Y, Zs. We can actually compute them. We know how big they are because we can just generate them all and then count how many numbers we get, right? So the values of this thing is going to be between 68 and 73. And again, this capital X here is just ranging between the little x and 2 times little x, right? So for each of the n's that appear between 68 and 73, we can study the distribution of pi of x plus y minus pi of x, okay, over all the x, which give us a fixed size for our sieved interval. Okay, so we look at all the intervals where the size of this interval is size n, and we figure out how many primes did we get in that thing. That's what these blue spikes on this graph are actually demonstrating. Okay, so I'm going to zoom in a little bit. Maybe I won't focus on the endpoint here, because the endpoints are a little bit fishy sometimes. So here I'm just taking, we had our sieved interval, it has 70 integers in it. H is describing how many, sorry, my brain is, yeah, how many primes you arrive. So H is your y-axis. It's how many primes are in the interval that you're looking at. And this height is how many intervals you actually hit that value. How many intervals you found that you had H number of primes. Okay, so you can see that the blue lines form some bell curve, or looks to be a bit of a bell curve, right? So nice, we should expect that. The dashed line here is appearing at the expected value, the average, which is in this case 17.959. We've plotted what are the minimum results that appear in this particular interval, and also the global minimum that we expect for being x equals 10 to the 8, and same for the maximums. And then what's left, I haven't described to you, what is this red line? Okay, so the red line on this drawing is the binomial curve that would be generated given the modified Primek heuristic, right? So if I had those fixed probabilities based on the z and the everything that we just fixed up above, this is the binomial curve that we would get, this red line. So this was somewhat surprising data to run into, because you can see from this picture, and I'll show you a couple more pictures, that the red line is not as tall as the data, and it's fatter. It's fatter than the data is bearing out to be, so to speak. So this is a bit suspicious. You're thinking, okay, why? What's going on? Why is it so far away? And this actually persists if we take different intervals. Now I've chosen 69 and 72, but you can see the same behavior, that the red line does not peak at the same place, and it is fatter than the data, okay? So we have this table of the computed results. The expected mean given by the model is, between 17.4 and 18.6. The actual mean given by the data is between 17.6 and 18.5. So actually the means are pretty close. That's nice. It seems somewhat confidence-inducing, but the variances are really far away from each other. So the heuristic says that the variance should go between 12.95 and 13.9, but the data says that it doesn't even come close to 12 at any point in the intervals, no matter what. It's always much lower. So this is a point of curiosity. What's going on here? Why is this the case? And it turns out that Montgomery and Soundarajan wrote a paper in 2004 that can pretty clearly elucidate what's going on here, that in fact this variance being so weird is not such a big surprise. But if we change, instead of looking at the variance with what the prediction would suggest, we change it to look like this. Okay, so it has a few extra terms here. This is what the model says we should use, and this is what a paper of Montgomery and Sound says we should use. Then this new value gives us a variance of size 11.11. Okay, but that's really close to the data. It lines up very, very nicely. So it looks like, if we have to modify things, it's not the end of the world. Maybe instead of becoming binomial, it's going to be normal, where we have an understanding of the variance looking like this, and we can study that instead. But we haven't done that. That's maybe a new direction. So what's the problem for us is that even if we know this about the variance, we don't understand how to interpret this in terms of the tails of our intervals, right? Like, we were actually interested in the tail probabilities, what's going on in the maximum and the minimum. And even if we change this, we aren't 100% sure how that's going to affect the predictions of those things. And the second question that you might have about it is, like, maybe this assumption of independence is a little bit suspect because the data doesn't fit the graph. And those are things that we want to investigate later. And that is my last slide. I'm really sorry I went super far over time. So thank you.